you stand on a world that circles a modest star, separated from its neighbours by gulfs so vast that numbers lose meaning. Mars hangs nearby in your night sky, a silent ember drifting across the dark. You look at it and imagine the journey. A quick flight, a long cruise, perhaps a matter of months. Distance shrinks in your intuition because the planet is familiar, bright, and often visible with the naked eye. Compared to the stars, Mars appears close, almost within reach. But space distorts simplicity. The gap between two planets is not fixed. Their orbits carve shifting paths around the sun, stretching and compressing the space between you and that rust-colored world. What feels intuitive becomes misleading. Travel time is not determined by a straight line, but by mechanics, motion, and limits that do not yield to convenience. If you enjoy these cosmic journeys, please like and subscribe and tell us where in the world you are listening from. Let's begin. Mars drifts across your sky like a wandering light, but you do not chase it through darkness. You stand on an orbiting world, and your destination is another world doing the same. The distance between you and Mars stretches and contracts, never pausing. You may feel as if you could fly straight toward it, but the universe does not provide straight lines. Every approach is temporary, every alignment fleeting. You must first understand why the journey is never the same twice. From the ground, the Mars problem appears small. Two planets orbit one star, and the gap between them seems like a fixed number. But Earth and Mars are constantly in motion. They follow elliptical orbits, inclined at slightly different angles, moving at different speeds, never sharing the same position twice. Earth takes about 1 year to circle the Sun. Mars needs nearly 2. Even if you launched instantly, the moment your spacecraft leaves Earth, both planets continue on their trajectories. You are not aiming at a static world, but at a coordinate that slides forward every second. Because of this, there is no single distance to Mars. There is only distance at a specific moment. When Earth and Mars lie on the same side of the Sun, Mars stands in opposition. When the planets sit on opposite sides, Mars is in conjunction. These terms describe geometry, not convenience. At a favourable opposition, the two worlds can sit roughly 54 million kilometres apart. In a less favourable geometry, the gap can be more than 7 times larger. Mission planners cannot treat these extremes as trivia. They dictate the cost, duration, and feasibility of the journey. You might imagine that all oppositions are equal. They are not. Mars's orbit is noticeably more eccentric than Earth's. At different points in its path, Mars is closer or farther from the Sun. When opposition occurs while Mars is nearer its closest point, the distance between planets shrinks dramatically. When opposition falls near its farthest point, the separation expands. Two alignments that appear similar on a calendar can represent entirely different voyages in space. Transfer times stretch or contract, not because spacecraft change, but because orbital geometry does. This shifting distance shapes everything humans send outward. Space agencies do not choose launch windows to satisfy schedules. They wait until Earth and Mars fall into an efficient alignment. That alignment repeats roughly every 26 months, when the angular relationship favors an energy-saving trajectory between orbits. Miss it, and the next reasonable attempt lies more than 2 years in the future. The universe does not offer continuous access. It provides narrow gates that open and close according to motion alone. A spacecraft traveling between planets does not point directly at Mars. It departs Earth on a curved path that gradually expands outward from the Sun. The Sun's gravity defines this curve. The vehicle follows a trajectory that intersects Mars's orbit at a future moment, not Mars's current position. Arrival is not a place. It is a synchronization of time and motion. If the craft reaches the orbit too soon, the planet has not arrived. If it reaches too late, Mars has already passed. The geometry is exact, and the planet will not slow down to meet an incoming visitor. This is why the journey is never reduced to a single number. When textbooks list average distances 78 million kilometers, 225 million kilometers, they are simplifications. Averages erase the most important fact. The solar system is dynamic. Every mission must account for this motion. Engineers simulate thousands of paths, adjusting parameters to match the rhythm of two orbiting worlds. They do not choose routes based on personal preference or idealized straight lines. They choose paths that exist within the constraints of celestial mechanics. To travel from Earth to Mars is to navigate a moving framework. Space does not offer you the certainty of fixed destinations. It gives you shifting targets governed by gravity and time. Before you consider engines, fuel, or humans aboard a ship, you accept this principle. You travel between worlds that never stop moving. From your vantage point, Mars looks closer than Jupiter, closer than the glittering stars beyond. It moves quickly among constellations, sometimes bright enough to paint a visible path. You might believe that the closeness you see is a clue to the ease of travel, but sight compresses distance. Your brain evolved to gauge horizons in forests and valleys, not orbits spanning tens of millions of kilometers. Mars is near, yes, but only in the language of the cosmos, not in the language of instinct. Human perception treats the sky as a flattened dome. Stars appear arranged on a single surface, and any object that wanders among them seems to sit on that surface too. Mars moves from night to night because Earth and Mars trace different paths around the Sun. Your eyes interpret that motion with a familiar rule. Things that move against their background must be closer than things that remain still. This rule works on a hillside or across a field. It fails in a cosmos where all motion is orbital rather than local. Mars does not drift because it is near. It drifts because two planets circle the same star at different rates. The Moon reveals how distance should feel. It is large enough to show a disk, bright enough to cast shadows, and close enough to drift perceptibly across the horizon in a single evening. A spacecraft can reach it in a matter of days. Mars, even at its brightest, remains a pinprick of reflected sunlight. The Moon is hundreds of thousands of kilometers away. Mars sits tens of millions of kilometers away at minimum, and far farther at other times. The difference in travel time is not a matter of technology, it is the consequence of spatial geometry. Numbers offer clarity where instinct cannot. Astronomers describe distance using light travel time because kilometers quickly lose intuitive meaning. When Earth and Mars move closer in their orbital dance, light crossing the separation takes only a few minutes. When they drift apart toward conjunction, that same journey can take more than 20 minutes. These delays are not academic. They define how missions function. Instructions from Earth arrive long after they are sent. Confirmation returns long after actions are executed. A spacecraft en route to Mars cannot be steered as a pilot steers an aircraft. It must operate through pre-planned steps, autonomous reactions, and scheduled corrections. Brightness can confuse things further. When Mars approaches opposition, it often glows brighter than most stars you can see. Bright objects feel nearby because proximity usually increases illumination on Earth. In space, brightness depends on reflection. Mars reflects sunlight from dust and rock. Jupiter, though much farther away, often rivals or exceeds Mars because its vast atmosphere scatters sunlight efficiently. Venus, even closer to the Sun, becomes brighter still because its cloud deck acts as a mirror. Your eyes cannot separate these physical factors. They respond only to what reaches them. Even motion patterns can deceive. When Earth overtakes Mars in its orbit, Mars appears to slow, reverse direction, and then regain its forward drift. This retrograde arc is not Mars reversing course. It is a perspective effect created by two bodies moving along curved paths at different speeds. Nothing about it suggests proximity. It simply reveals how the frame of reference shifts as Earth completes its faster loop around the Sun. Space lacks the depth cues your nervous system expects. There is no familiar haze to soften faraway shapes, no terrain to scale foreground against background. Mars floats alone, unattached to context. Without measurement, there is no way to sense how far it truly is. Recognizing the illusion prepares the next step. If distance cannot be trusted by sight, then only orbital motion can determine how worlds meet. If you could freeze the solar system, you might imagine launching directly toward Mars. Your planet spins, Mars spins, and both whirl around the Sun in paths that never align perfectly. You are chasing a moving target while you yourself are moving. The geometry is dynamic, not static. To travel between such worlds, timing becomes more important than thrust. The solar system is a system of constant motion. Earth traces one orbit around the Sun every 365 days, while Mars requires nearly 687. These periods determine how the two worlds approach and separate. Their relative positions never repeat in a simple cycle because their speeds and orbital shapes differ. This means there is no permanent distance, no fixed midpoint, and no single direction that always leads outward. Every point on Earth follows a curved path, and so does every point on Mars. A spacecraft must begin its trip inside this moving framework, not above it. Launching directly toward where Mars appears in the sky would fail because the planet would leave that location long before arrival. The journey must be designed around where the planet will be, not where it currently is. Orbital mechanics reflect the conservation of energy rather than the convenience of straight lines. When a spacecraft departs Earth, it carries Earth's orbital velocity with it. That velocity is not an obstacle, it is an advantage. Instead of cancelling motion, the spacecraft uses it. Engines provide additional speed to reshape its path around the Sun, forming an elliptical trajectory that intersects Mars's orbit. This transfer does not resemble a thrown stone. It resembles a curve drawn inside a gravitational field. The Sun dictates the shape of that curve, and engineers calculate the exact timing necessary to meet another world at the intersection point. The spacecraft is not chasing Mars, it is meeting it along a shared orbital corridor. The alignment needed for efficient transfer occurs only during certain periods. When Earth and Mars occupy complementary phases in their orbits, a launch window opens. Within this window, a spacecraft can follow a path that requires minimal energy because the geometry of the solar system itself assists. Outside the window, trajectories become longer and fuel demands increase sharply. The planets do not create these windows intentionally. They arise from the mathematics of motion. A launch too early or too late forces the spacecraft to spend energy correcting for a misaligned rendezvous, extending the trip beyond practicality. Planetary rotation creates additional complexities. Earth spins eastward, giving launches from lower latitudes a helpful boost. A rocket launched in that direction adds Earth's surface velocity to its own. This advantage may seem small compared to orbital speeds, but even a few hundred meters per second matters. Mars also rotates, and its rotation affects arrival. A spacecraft must approach a region of the planet that is turning beneath it, adjusting its path to avoid overshooting or striking the atmosphere at an unstable angle. These calculations are not dramatic, they are routine consequences of a universe in motion. Gravitational influences further shape travel. A spacecraft leaving Earth transitions from the planet's gravitational well to the Sun's. At no stage does gravity disappear. It changes its dominant source. The Sun dictates deep space movement, while Earth and Mars influence the beginning and end of the journey. Engineers design trajectories that bend through these gravitational fields, minimizing propulsion and maximizing the natural tendency of bodies to follow curved paths. Flight is not a battle against gravity, it is navigation within it. Once motion is understood, the next step becomes clear. There is an optimal path through this moving system, one that balances time and energy more efficiently than any other. There are moments when Mars stands opposite the Sun in your sky, glowing brighter, coming closer. There are others when it hides behind the Sun, distant and unreachable. These events are predictable, like seasons. yet they alter everything. A journey begun at one moment could be wildly inefficient at another. Where Mars sits in its orbit determines the very shape of the path you must take. Opposition describes the alignment in which Earth lies between Mars and the Sun. In this configuration, the two planets are positioned on the same side of the star and are, on average, closer than at any other time. Conjunction describes the opposite arrangement. Mars lies beyond the Sun from Earth's perspective. The two terms do not convey emotion or preference. They define geometry. Because transfer trajectories depend on relative position, these alignments determine the energy required to depart one orbit and intersect another. An opposition window does not guarantee the shortest possible distance, but it establishes the lowest general energy cost for missions relying on conventional propulsion. A conjunction period, by contrast, places Mars far away along its orbital track, demanding high velocities and extended travel. Mars does not orbit the Sun in a perfect circle. Its path is more elliptical than Earth's. That difference creates variations in minimum approach distance during each opposition. When opposition occurs near Mars's perihelion, the moment when the planet is closest to the Sun, the two orbits draw significantly nearer. These events are called perihelic oppositions. They can shrink the separation between Earth and Mars to roughly 54 million kilometers. When opposition occurs near Mars's aphelion, the moment when it is farthest from the Sun, the separation increases substantially. The difference is not just numerical. Propulsion models show that even moderate changes in distance influence burn requirements and transit duration. A launch that seems similar from a calendar perspective may result in very different mission characteristics when these orbital effects are considered. These cycles recur, but not identically. Mars needs nearly 2 Earth years to complete an orbit. Earth completes one in a single year. Because of this mismatch, their alignments drift forward each time. The interval between favorable transfer opportunities averages around 26 months, during which a spacecraft can follow a low-energy elliptical path known as a transfer trajectory. The window is not a precise moment. It is a period defined by when launch velocity and planetary geometry combine to guide a spacecraft from Earth's orbit to Mars's orbit without demanding excessive course corrections. Mission planners model these intervals far in advance because missing them forces the adoption of alternative trajectories that require more fuel or result in inefficient arrival conditions. At conjunction, the situation reverses. Mars lies on the far side of the Sun at angles that stretch the distance to hundreds of millions of kilometers. Transfer paths initiated at these positions must span longer orbital arcs, absorbing additional energy to achieve interception. Communication with spacecraft already en route can also be complicated. Not because the Sun blocks physical motion, but because solar plasma and electromagnetic noise interfere with radio signals used for navigation and telemetry. The risks are operational rather than catastrophic, but they are sufficient to discourage mission launches near conjunction. Most agencies avoid placing spacecraft in critical mission phases when geometric alignment causes extended signal disruption. Opposition and conjunction illustrate how travel to Mars is governed not by raw enthusiasm or propulsion alone, but by celestial timing. They set the rhythm of opportunity and constraint. Recognizing these alignments leads naturally to the next question. Once an efficient window is chosen, how does a spacecraft actually move between orbits? You may imagine pointing a rocket straight at Mars, but spaceflight prefers curves. The most efficient journeys do not resemble arrows. They resemble spirals and arcs. 2 planets orbiting a star require trajectories that nestle into gravity's rhythm. You begin by falling outward, not lunging forward. The shortest path in energy is not the shortest path in time. The Hohmann transfer is the simplest and most studied method of traveling from one orbit to another using the least energy. It is built upon the principle that orbit changes are best accomplished through controlled impulses, not constant thrust. A spacecraft already traveling around the Sun shares Earth's orbital speed. Rather than cancelling that motion, it uses it as the foundation for a new elliptical path. The craft performs a burn to raise the farthest point of its orbit outward until it intersects Mars's orbit. Once there, a second burn circularizes the trajectory to match the motion of Mars. The technique is elegant because it leverages the Sun's gravity rather than fighting it, transforming orbital momentum into a bridge between worlds. This method is not quick. The Hohmann transfer requires months of coasting along an elongated ellipse. The spacecraft spends most of this time under no active propulsion, drifting toward its destination like a bead sliding along a curved rail. The duration arises from geometry, not from lack of technological ambition. When two bodies orbit the same star, the lowest energy way to reach the outer one is to allow the spacecraft to drift outward at a rate that balances gravitational pull with forward momentum. Faster travel is possible, but it demands significantly more fuel. The Hohmann model demonstrates how celestial mechanics extract cost in time when fuel reserves are limited or payload mass is high. Each of the two burns in the Hohmann transfer serves a distinct purpose. The first, called the departure burn, increases the spacecraft's velocity relative to the Sun, lifting its orbit from Earth's circular path into an ellipse. The ellipse's closest point remains near Earth's orbit, while its farthest point touches Mars's orbit. The timing of this burn determines where the spacecraft will intersect Mars's path later. If performed too early or too late, the resulting ellipse will overshoot or undershoot the rendezvous point. After months of transit, the second burn slows the craft to match the orbital speed of Mars. Without this braking action, the spacecraft would continue along the ellipse and drift away. Capturing the craft into Mars's orbit or allowing it to enter its atmosphere requires aligning velocity, not just position. The transfer also reveals why launch windows are central to mission planning. The spacecraft must begin its journey when the planetary geometry allows the transfer ellipse to intersect Mars's orbit at the appropriate moment. Mars must reach the same location in its orbit when the spacecraft arrives. This is the reason missions depart every 26 months. During this interval, Earth and Mars form the angular relationship necessary for the outward ellipse to connect their orbits. If the planets are badly positioned, the same principle still applies, but the required burns become inefficient. The craft must accelerate harder to compensate for poor timing, which increases costs and reduces available payload. While theoretically ideal, the Hohmann transfer assumes a simplified, two-body model, a spacecraft orbiting a star and aiming for another planet. In reality, gravitational influences overlap. Earth's gravity initially dominates, then yields to the Sun, and later gives partial control to Mars. These transitions create small deviations from the ideal ellipse, requiring periodic corrections. Such adjustments are not flaws. They are a natural consequence of flying within a multi-body system. Mission designers calculate these corrections in advance, incorporating margins to ensure the spacecraft remains on its intended track. Understanding the Hohmann transfer clarifies how engineers use gravity instead of resisting it. It also leads naturally to the next question. Why would anyone choose a faster, more costly path when a slower one already works? There are ways to shorten the voyage. You could burn more fuel, accelerate harder, bend your path with force rather than waiting for orbital harmony. The travel time shrinks, but the cost rises exponentially, and the stresses imposed on a spacecraft multiply. Speed is not free, and space does not forgive inefficiency. A high-energy trajectory behaves differently from a classical transfer. Instead of modifying an orbit gently, a spacecraft applies additional thrust to increase its heliocentric velocity. This added energy allows the vehicle to reach Mars's orbital distance sooner. Shorter travel occurs because velocity better resists the Sun's gravitational pull, letting the spacecraft climb outward faster. The method does not eliminate the need for timing, because Mars must still be present at the point of intersection, but the allowable launch window broadens. Such trajectories are favored when payloads must arrive quickly, or when mission profiles demand reduced cruise duration. They are not solutions without consequence. The core penalty appears in the rocket equation. To increase spacecraft speed, more fuel is required. Propellant increases mass, and mass increases the energy needed to accelerate. Every kilogram added to the initial fuel supply demands more fuel to lift it from Earth and more fuel to accelerate it later. The relationship compounds. A modest reduction in transit time can require a dramatic increase in launch mass or engine performance. The challenge is not conceptual but physical. Rockets that attempt to outrun efficiency must carry more propellant than they can reasonably transport, or else sacrifice payload and redundancy. The problem is not design failure, it is fundamental mathematics. High-energy paths also alter thermal and mechanical environments. Spacecraft structures are engineered to endure long periods of quiet coasting, interrupted only by short correction burns. A mission that uses aggressive acceleration imposes different stresses. Engines operate longer, heat accumulates, and vibration increases. Tanks, plumbing, electronics, and attitude control systems must withstand extended loads. These conditions do not inherently threaten safety, but they increase engineering complexity. The vehicle must be designed with margins that anticipate more persistent thrust. Each added margin increases mass, feeding back into the same fuel mass spiral. Mission planning reflects similar challenges. A spacecraft traveling quickly cannot coast passively into Mars's influence. It will arrive with greater relative velocity and must be slowed more aggressively to capture into orbit or descend. The arrival burn becomes significantly larger, and its timing becomes more sensitive. If the spacecraft underestimates deceleration, it risks flying past Mars entirely. If it overestimates, it may expend unnecessary fuel or enter an unstable orbit. High-energy travel compresses mission uncertainty into shorter periods, giving engineers less time to diagnose errors and fewer opportunities to correct them. Navigation becomes a sequence of tightly constrained windows. For robotic spacecraft, these penalties are measurable and manageable. Scientists may choose to pay the cost when urgency outweighs efficiency, for example, to reach seasonal targets or avoid environmental conditions on the Martian surface. For human missions, the calculus shifts. Faster travel reduces radiation exposure and psychological strain, but it also requires larger engines and more fuel, which expand risk in other areas. Additional mass demands stronger launch vehicles. Greater acceleration forces require more robust structure. Larger arrival burns impose higher thermal loads and tighter descent envelopes. Choosing speed means accepting complexity across the entire mission architecture. Continuous thrust systems are sometimes proposed as alternatives. They offer gentler acceleration sustained over weeks or months, gradually building velocity rather than producing brief impulses. Ion drives and solar electric propulsion exemplify this model. They require very little propellant mass, but demand electrical power and time. The spacecraft accelerates slowly, accumulating speed beyond what chemical engines could manage on short burns. Transit time may shrink, but the energy must be supplied continuously. These methods improve efficiency relative to conventional rockets, yet still face trade-offs. Power supply systems add mass, and thrust levels limit initial maneuvering capability. The mission profile becomes one long balancing act. The tension between rapid arrival and manageable cost underscores a central reality. Greater speed always carries a price, expressed in mass, energy, or complexity. Accepting this truth marks the transition into the next question, which asks not how quickly one can travel, but when departure should occur to minimize the price altogether. You cannot leave for Mars whenever you choose. Launch at the wrong moment, and you chase a planet that moves faster than you can catch it. Launch too early, and you overshoot it entirely. The window opens like a gate, narrow and precise, lasting only weeks. You must wait for alignment, not desire. A departure window emerges from the orbital synchronization of Earth and Mars. Each planet circles the Sun with its own period, speed, and orbital shape. Earth completes a revolution in about 365 days, while Mars needs nearly 687. Because Earth moves faster, it periodically catches up to Mars in a way that allows a spacecraft to be launched into a path intersecting Mars's orbit later in time. This repeating pattern is governed by the synodic period, the time it takes for two bodies to return to the same relative configuration. For Earth and Mars, this period averages around 26 months. Launching during this interval allows a spacecraft to follow a low-energy trajectory that uses orbital geometry rather than continuous thrust to reach its destination. The window is not a single date. It is a span of days during which the required change in velocity, expressed as delta V, remains within an acceptable range. At the center of the window lies the most efficient moment. As launch dates move earlier or later, delta V requirements increase. Engineers plot these variations as curves, revealing shallow valleys of opportunity surrounded by steep slopes of inefficiency. A mission launched too far from the ideal point would need more fuel to achieve the same outcome. Additional fuel either reduces payload capacity or demands a heavier launch vehicle. The window therefore protects a mission's practicality by controlling mass and energy simultaneously. This timing is rooted in prediction rather than approximation. Planetary positions, years or decades into the future, are calculated using precise ephemerides. These datasets describe where planets will be at specific times with extraordinary accuracy. Mission planners use them to identify windows, then refine launch targets to align spacecraft arrival with Mars's future location. Since the spacecraft travels for months, its destination must be anticipated ahead of time. The vehicle is not aimed at Mars's visible position, but at the point Mars will occupy when the spacecraft's elliptical path intersects its orbit. The window also considers rotational motion. Earth's rotation allows rockets launching eastward from equatorial or low-latitude sites to benefit from tangential surface velocity. This incremental boost reduces the energy required to reach orbit. The effect does not change the existence of the window, but it influences the total delta V needed at launch. Arrival must also respect rotation. Mars rotates beneath incoming spacecraft, so orbital insertion trajectories are calculated relative to planetary spin. The window determines when the journey can begin. Rotation determines how it must end. Launch timing is not immune to operational constraints. Weather at the launch site, readiness of ground support systems, and performance margins of propulsion stages influence the choice of specific days within the window. A mission may have multiple acceptable dates, sorted by how much energy they require. When unexpected delays occur, planners must evaluate whether to launch later in the window, accept increased fuel demands, or postpone until the next cycle. Postponement carries weight. Missing the window can shift departure by more than 2 years, altering budgets, staffing, and technology availability. The planets provide an opportunity, but agency schedules must align with natural rhythm. The departure window exemplifies how interplanetary travel depends on timing rather than effort alone. Once alignment is chosen and fuel budgets are set, the path to Mars unfolds along curved routes shaped by gravity and geometry, not by straight lines. You might imagine crossing the void in a straight line, pushing forward like an arrow through darkness. You might imagine speed as a line segment, shortest between 2 points. But in the solar system, straight lines rarely exist. Every world bends space through gravity, and every path must yield to the rules of mass and motion. Journeying to Mars is not a sprint, it is a curve. Interplanetary travel unfolds within gravitational fields. A spacecraft leaving Earth begins in a heliocentric orbit, not a blank expanse of emptiness. It already moves around the Sun at nearly 30 kilometers per second, carried by the same orbital motion that governs Earth itself. When propulsion raises its velocity, it stops following Earth's orbit and begins tracing a new ellipse around the Sunday. The spacecraft does not fly directly toward the planet it seeks. It follows a pathway defined by how much energy was applied and how the gravitational environment bends its motion. The path curves outward and meets Mars's orbit only at a specific time, when the spacecraft and planet occupy the same region of space. Curvature is not an inconvenience. It is the natural result of Newtonian mechanics. Objects in space move in continuous free fall under the influence of gravity. For a spacecraft entering a transfer orbit, the Sun is the dominant source of gravitational pull. The spacecraft follows the curve imposed by that pull, with propulsion providing short impulses that shift its trajectory. After a burn, the craft coasts, its motion determined by mass, momentum, and distance from the sunday. The spacecraft's engines do not remain active throughout the voyage because gravity supplies the acceleration and deceleration needed along most of the path. The fuel used to reshape the orbit is far more valuable than fuel spent attempting to override these forces. Curved travel also enables stability. A spacecraft that continuously thrusts toward Mars would quickly exhaust its propellant and still fail to hold a direct path. Minor deviations accumulate, steering errors compound, and corrections become increasingly expensive. By following a gravitationally permitted curve, navigation becomes predictable. Mission teams model expected positions, compare measured telemetry to those models, and perform small course corrections when necessary. These corrections require tiny bursts of thrust, often lasting only seconds, to adjust the spacecraft's orientation or velocity. They do not redefine the entire mission. They maintain alignment within the planned orbital arc. Mid-course corrections illustrate how curved travel operates in practice. Over months, subtle influences, solar radiation pressure, gravitational perturbations from other bodies, and imperfections in initial burns nudge the spacecraft away from its ideal path. These deviations are small, but interplanetary distances magnify them. A drift of fractions of a millimeter per second can become thousands of kilometers by arrival. Ground controllers monitor trajectory data, usually gathered through radio ranging and Doppler measurements, and schedule correction maneuvers at times when small changes have the most effect. Each correction is designed to preserve the geometry of the transfer, not to force a new route. Travel along curved paths also influences arrival dynamics. A spacecraft approaches Mars with momentum inherited from months of orbital motion. Its velocity relative to the planet is not arbitrary. It reflects the energy of the transfer orbit. To insert into Martian orbit or begin descent, the spacecraft must shed some of this energy. Orbital capture burns, atmospheric entry, or aerobraking accomplish this reduction. These steps do not end the curvature of travel. They replace one curve with another, transitioning from a solar ellipse into a Martian one. Understanding curved motion clarifies why interplanetary navigation resembles choreography rather than pursuit. Paths are not drawn against a backdrop of emptiness. They emerge from gravitational structure established long before spacecraft existed. The craft does not conquer the solar system. It joins a pattern already in motion. Accepting that pattern prepares the way for the next consideration. Even with a stable path and predictable arrival, distance itself defines how long the journey will take. You coast for months across an empty gulf. Mars grows incrementally brighter, not because you accelerate, but because distance shrinks. The trip is not a dash. It is a glide through a gravitational system. You drift, not toward your destination, but along the path that will eventually take you there. Time is the currency spent on the route geometry. Transit duration results from orbital mechanics and chosen trajectory. A spacecraft on a Hohmann transfer spends most of its journey coasting along a solar ellipse that expands away from Earth's orbit and approaches Mars's. Velocity decreases as the spacecraft climbs the Sun's gravitational gradient. The elliptical curve ensures arrival, but only after months of travel. Typical durations for such missions range from 6 to 8 months, depending on the launch window and the minimum energy path selected. These estimates are not determined by technological limitations alone. They reflect the energy budget imposed by the departure geometry, the mass of the spacecraft, and the gravitational environment through which it moves. During this phase, the spacecraft travels through interplanetary space, where forces are subtle but persistent. Solar gravity dominates overall motion, shaping the arc of flight. Smaller influences, solar radiation pressure, gravitational nudges from planetary bodies, and asymmetries in spacecraft mass distribution slowly accumulate. The craft's onboard navigation system monitors its trajectory using star trackers, inertial sensors, and radio signals exchanged with ground-based stations. Corrections are small, measured in fractional meters per second, because the goal is not to alter the path but to maintain the intended ellipse. These adjustments preserve long-term accuracy without consuming excessive fuel. Transit duration also depends on initial launch energy. A spacecraft launched with greater speed can shorten travel time by flattening the elliptical arc or adopting more aggressive transfer profiles. However, increased energy demands require more propellant, heavier launch vehicles, or reductions in payload mass. These trade-offs are well understood in mission planning. When launch energy is lowered to preserve mass, travel duration stretches accordingly. The spacecraft remains within predictable bounds, but the journey lengthens. This balance between time and fuel is fundamental to interplanetary mission design and drives decisions long before launch occurs. Communication across the Gulf introduces measurable delays. Radio signals travel at the speed of light, but even light requires minutes to cross the Earth, Mars distance during transit. Mission teams operate under a cadence imposed by physics. Send instructions, wait for spacecraft telemetry, analyze responses, and schedule subsequent actions. This cadence does not significantly alter the spacecraft's travel time, but it influences how navigation and operations are managed. Remote guidance cannot rely on instantaneous input. It works through carefully sequenced updates that respect the nature of interplanetary distance. Thermal conditions during transit remain relatively stable. The spacecraft is far enough from the Sun to avoid extreme heating, yet close enough to receive adequate solar power if its systems rely on panels. Radiators dissipate heat from instruments, and insulation protects sensitive components. These measures support months-long travel without requiring frequent intervention. Systems remain active but unhurried, maintaining health while the spacecraft follows its curvature through space. Transit duration also influences arrival geometry. A spacecraft that reaches Mars earlier or later than planned faces different orbital positions and velocities. The planet's location along its path determines how much deceleration is required to match its motion. If the craft arrives with excess speed, insertion burns must be larger to achieve orbit. If it arrives slower, burns may be reduced, but timing becomes more sensitive. Precision in transit prevents these outcomes from becoming problematic. Engineers set flight timelines well before launch to ensure the spacecraft encounters Mars at the correct relative velocity. Long interplanetary cruises demonstrate a fundamental reality. Distance is not defeated by raw acceleration but managed through predictable motion. The months spent traveling are not wasted time, they are structural elements of the method itself. Accepting these spans naturally leads to the next concern. Once arrival begins, how does a spacecraft slow down and enter the orbit of the waiting world? There are times when Mars drifts across the Sun's far side, more distant than any human spacecraft has ever traveled. The gulf becomes absurd, hundreds of millions of kilometers. You could send a message at the speed of light and watch it take minutes to arrive. You begin to understand why windows matter. When Mars lies on the opposite side of the Sun from Earth, the planets occupy a configuration known as solar conjunction. In this state, the distance between them reaches one of its greatest values. The exact number varies from cycle to cycle because Mars follows an eccentric orbit, but separations of 350 to 400 million kilometers are typical during these periods. The geometry stretches the communication path between planets to its longest practical length, and even signals moving at light speed face noticeable delays. A message sent from Earth must travel toward the Sun, curve around it from the spacecraft's perspective, and then continue outward until it reaches Mars. The finite speed of light transforms planetary distance into operational consequences. At such separations, spacecraft experience long communication cycles. A command issued from Earth may require more than 20 minutes to reach Mars. Telemetry returning to Earth adds another 20. A full round of interaction, from sending instructions to receiving responses, can consume nearly an hour. These delays shape mission design and operations. Navigation does not function through real-time steering. Landers do not descend under direct human guidance. Engineers program sequences in advance, trusting automated systems to execute steps with precision before confirmation arrives. The distance makes autonomy a requirement rather than a convenience. Conjunction is more than distance alone. The sun's electromagnetic environment complicates communication. Radio waves passing near the solar atmosphere can scatter, distort, or vanish in transient interference. Mission teams often reduce activity during conjunction to avoid misinterpretation of corrupted data or commands that might trigger unintended actions. Engineering protocols designate safe modes, in which spacecraft perform minimal tasks while light from the sun disrupts communication channels. The pause is not dramatic. It is procedural. Spacecraft wait patiently while the geometry improves, then resume operations when signals become reliable. These conditions demonstrate why spacecraft rarely depart for Mars when the planet is near conjunction. Launching under such circumstances would force the journey to begin with maximal distance and minimal communication confidence. Transfers would require higher initial energy to compensate for unfavorable geometry. Arrival would occur months later, potentially after additional windows had been missed. Mission complexity cascades from a single decision. Instead, planners select windows when the paths between orbits are shorter, energy costs are lower, and communication infrastructure remains dependable. The difference is not philosophical, it is quantitative. Even robotic missions feel the consequences of farthest separation. Deep space probes require periodic trajectory updates to counter small deviations. During conjunction, those updates stall. The spacecraft continues along its path, but adjustments cannot be confirmed immediately. Teams must wait until solar interference subsides. This delay can introduce additional correction maneuvers later, compensating for accumulated drift. The corrections are small, yet they illustrate how distance imposes discipline. Systems must be resilient, steady, and tolerant of periods without oversight. The numbers underscore the scale involved. Earth's atmosphere ends within 100 kilometers. The Moon lies within 400,000. Mars at conjunction may sit more than 1,000 times farther than the Moon. These gaps are not intuitive because the night sky offers no parallax or horizon. Human senses cannot detect the separation. Only measurement reveals it, transforming space into a domain where physics replaces instinct. Understanding this scale is essential when designing craft, calculating fuel loads, and anticipating signal travel times. The farthest positions of Mars remind mission planners that distance is not incidental. It defines how communication functions, how spacecraft operate, and how launch windows are chosen. With the concept of separation solidified, the next step considers how spacecraft must slow down to integrate into Mars's gravitational sphere once the long transit ends. Your journey is not a straight flight, it is a trade with the sun itself. Every motion, every burn, every correction interacts with a gravity field that dominates all smaller choices. You are not traversing an empty highway but weaving through a system of influence. Accepting this frame is the first step toward realistic travel times. Trajectories in the solar system are agreements with gravity rather than simple lines drawn between destinations. A spacecraft begins its existence bound to Earth, held within a gravitational well that requires energy to escape. When it rises beyond Earth's sphere of influence, it does not enter a neutral void. Instead, it transitions into a larger gravitational domain dominated by the Sunday. From that moment onward, the spacecraft becomes an object in solar orbit. The engines it carries no longer fight Earth's pull. They reshape the craft's motion around the star. Every adjustment is measured against the sun's overwhelming influence, which sets the baseline for the rest of the journey. This gravitational structure explains why interplanetary trajectories bend. Newtonian mechanics dictates that any object moving through a gravitational field follows a curved path unless propelled continuously to counter that curvature. Spacecraft lack the capacity to burn fuel indefinitely, so their journeys must be designed around arcs created by gravity. Mission planners compute these arcs mathematically as solutions to the restricted three-body problem, where the spacecraft's mass is small compared to the bodies that influence it. The Sun provides a central pull, while Earth and Mars supply local perturbations that adjust the curve subtly. The craft's engines are used sparingly to reshape or refine the curve, not to brute force a route. The Sun's gravity dominates because its mass dwarfs every other body in the system. Earth and Mars tug on spacecraft only weakly by comparison. When a mission leaves Earth's orbit, the Sun immediately becomes the principal force shaping motion. This transition is not abrupt. It occurs gradually as the spacecraft moves outward. Engineers refer to spheres of influence to describe the regions in which a planet's gravity controls motion more strongly than the Sun's. Within Earth's sphere, orbital mechanics resemble those of a satellite. Beyond it, the Sun governs the trajectory. Recognizing this boundary prevents misinterpretation of the spacecraft's true path. Every burn is therefore a negotiation. Ignition changes velocity, altering the shape and size of the heliocentric orbit. A short burn can raise the spacecraft's aphelion, moving its farthest point outward toward Mars's orbit. A later burn can adjust the perihelion or fine-tune arrival timing. Even course correction maneuvers are designed with gravity in mind. Tiny changes, applied early, compound over months of coasting. Mission planners prefer maneuvers at points of high leverage, such as near perihelion, because a small impulse there modifies the trajectory more efficiently than an identical impulse applied elsewhere. The goal is not to overpower gravity, but to cooperate with its predictable influence. Gravity also determines what happens upon arrival. As the spacecraft approaches Mars, it enters a region where Mars's gravity increasingly competes with the Sun's pull. The balance shifts gradually until the spacecraft falls under Mars's dominance. Mission profiles exploit this shift through carefully timed burns. If insertion into orbit is required, engines must reduce velocity so the spacecraft becomes gravitationally bound to the planet rather than flying past it. If atmospheric entry is intended, the craft must intersect the upper atmosphere at a controlled speed and angle. Both outcomes rely on matching the spacecraft's trajectory to the gravitational characteristics of the destination. Understanding trajectory as a gravitational negotiation reframes the entire journey. Distance, velocity, and timing are not separate variables. They are coupled outcomes of movement within a single dynamic field. Recognizing this interplay prepares the foundation for the next consideration. Once a spacecraft reaches Mars's sphere of influence, it must still slow down enough to remain there. As you drift outward, the Sun's pull weakens but never disappears. Your spacecraft must constantly negotiate with this invisible force. It shapes the arc of your flight, stretches your timeline, and constrains your options. No mission leaves the Sun behind. The Sun's gravitational field defines the environment through which every interplanetary mission travels. Its mass accounts for the overwhelming majority of material in the solar system, dominating the motion of planets, asteroids, and spacecraft alike. Even when a vehicle leaves Earth and moves toward Mars, it does so within a gravitational basin centered on the star. Earth and Mars do not operate as isolated wells of gravity floating in space. Their spheres of influence exist within the larger solar field, and spacecraft entering or exiting those regions continue to respond primarily to the Sun's attraction. This hierarchy explains why interplanetary paths curve instead of forming straight radial lines from one world to another. As a spacecraft moves outward, the Sun's pull weakens with distance, but only in a predictable and gradual way. The inverse square law governs the strength of gravitational attraction. Double the distance, and the force falls to 1/4. But even at Mars's orbit, the Sun's pull remains stronger than the planet's. A spacecraft traveling toward Mars is not captured suddenly. It experiences a slow transition in dominance from the Sun to the planet. Mission designers use this gradient to shape both the outbound trajectory and the arrival sequence. Understanding how force changes over distance prevents the misconception that deep space is a zero-gravity environment. It is a zone of continuously shifting gravitational balance. Solar influence also sets limits on travel time. A spacecraft on a low-energy path must follow an orbital ellipse that reflects the gravitational field through which it moves. Velocity increases when the vehicle is nearer to the Sun and decreases as it climbs outward. This phenomenon, known as Keplerian motion, defines why transfer orbits take months. Spacecraft cannot maintain high speeds without additional propulsive energy, and adding that energy requires significant fuel. The Sun's gravity therefore acts as a regulator on motion, stretching travel time in exchange for reduced fuel mass. The curve of the transfer orbit is not an inefficiency, it is the most practical response to the Sun's persistent pull. Solar radiation introduces a secondary influence. Photons streaming from the Sun exert pressure on spacecraft surfaces. Though extremely weak compared to gravity, radiation pressure becomes relevant over long voyages. Solar sails rely on this effect intentionally, while conventional spacecraft experience it as a subtle drift. Mission planners account for radiation pressure in trajectory calculations, adding corrective maneuvers to counter its cumulative effect. These maneuvers do not overpower gravity. They maintain alignment with the planned orbit. Even small sustained forces can displace a spacecraft significantly over the span of interplanetary flight. Magnetic and particle environments reflect the Sun's influence as well. The solar wind, composed of charged particles, extends beyond the orbit of Mars and shapes the electromagnetic conditions through which spacecraft travel. Electronics must be shielded to prevent interference or degradation, and communication systems must adapt to plasma-induced distortions. These considerations are not typically visible to the public, yet they inform hardware design and cruise operations. The spacecraft remains immersed in an environment defined by the star, not simply passing through void. Every maneuver during cruise occurs relative to the Sun's gravity. Course corrections align the spacecraft with its intended arc, not because the vehicle loses aim, but because gravitational and environmental effects accumulate gradually. Mission controllers schedule these adjustments at times when small impulses produce the greatest benefit, often when the spacecraft is moving fastest. In those regions, a minor change in velocity reshapes the overall path more efficiently. The relationship between velocity and gravitational position reinforces the importance of timing. Altering trajectory is always easier when the Sun's pull is strongest. The persistent presence of the Sun frames the final phase of the journey. As the spacecraft nears Mars, gravity from the planet begins to dominate locally, but solar influence still determines background motion. Capture maneuvers, atmospheric entry, or orbital insertion must be calculated in reference to both gravitational sources. Transitioning from one sphere of influence to another is not a sharp boundary but a gradual transfer of control. Recognizing this layered environment leads naturally to the next concern. Slowing enough to enter the Martian system, chemical engines roar, but their power is finite. They can lift a spacecraft from Earth, accelerate it into transfer, and provide small corrections. They cannot sustain relentless thrust for months on end. Mars lies within reach, but not at the pace of your imagination. Chemical propulsion has served as the backbone of spaceflight since the first orbital missions. It provides high thrust over short durations, allowing rockets to overcome Earth's gravity and reach escape velocity. Combustion of propellants, such as liquid oxygen and kerosene, or liquid oxygen and hydrogen, releases energy rapidly. This burst of power lifts payloads, stages, and spacecraft into orbit. Once there, smaller chemical engines shape initial trajectory by providing the velocity necessary to enter a solar transfer path. But chemical engines do not operate like terrestrial motors. They rely on finite propellant reserves, and their fuel mass increases dramatically when long burns are required. The spacecraft cannot carry enough fuel to accelerate continuously for months without compromising structural integrity or payload capacity. The limits of chemical propulsion are rooted in exhaust velocity. A rocket's capability is measured by its specific impulse, which reflects how efficiently it converts propellant mass into thrust. Typical chemical engines offer specific impulse values between 300 and 450 seconds in vacuum, depending on design and fuel chemistry. These values are suitable for launch and short maneuvers, but insufficient for interplanetary acceleration over large timescales. To halve the duration of a Mars transfer, a spacecraft would need to expend far more propellant than a chemical system could reasonably store. Every kilogram of additional fuel requires additional mass to lift it, creating a cascading and eventually prohibitive requirement. This is why spacecraft coast most of the way to Mars. After an initial burn sets the trajectory, gravity becomes the primary driver of motion. The craft does not attempt to outrun orbital mechanics. It moves through them. Chemical thrusters fire only when necessary, to correct minor deviations, adjust arrival timing, or perform insertion burns at the destination. Sustained thrust would not only consume excessive propellant, it would also alter trajectory in unpredictable ways. The spacecraft must remain stable over months, not behave as a continuously accelerated projectile. High-energy missions can shorten transit, but they magnify limitations. A direct injection trajectory increases launch energy, compressing travel time, yet demands significantly larger initial propellant mass. Even powerful rockets experience diminishing returns when trying to accelerate continuously. Increasing velocity by even small increments late in flight becomes expensive because the spacecraft must push against the diminishing but persistent gravitational pull of the Sun and the inertia of its own mass. These constraints are not engineering choices, they are physical realities defined by the rocket equation. Crewed missions intensify these concerns. Spacecraft designed to carry humans must incorporate radiation, shielding, life support, redundancy, and safety systems. Each of these elements increases mass. Every added kilogram raises fuel requirements or reduces payload capacity. Chemical propulsion cannot eliminate this constraint by simply burning harder. The physics of thrust, fuel, mass, and exhaust velocity impose boundaries that even advanced engines cannot easily break. Mission architecture must therefore accept slow transfers or incorporate propulsion alternatives. Hybrid strategies sometimes supplement chemical engines with auxiliary systems. Deep space missions may include small hydrazine thrusters for fine control or reaction control systems for attitude adjustments. These subsystems do not change the overall transfer pace. They maintain orientation, compensate for drift, and manage momentum after course corrections. Their efficiency lies in precision, not velocity. The chemical propulsion core remains responsible for major burns, typically at the start and end of the journey. Chemical propulsion represents a proven and reliable foundation, but its nature defines the rhythm of Mars missions. It provides decisive bursts of energy, surrounded by long periods of passive travel. It enables reach, not haste. Recognizing these limits leads toward the next question. If chemical engines cannot accelerate continuously, what propulsion approaches can sustain thrust over months? There are engines that whisper rather than roar. They push gently, constantly, for months. They turn acceleration into accumulation. These methods slice time from the journey, but they demand electricity, endurance, and trust in slow progress. In space, consistent motion can outperform violent force. Ion propulsion represents a different philosophy of movement. Rather than releasing chemical energy explosively, these systems heat or accelerate propellant to extremely high speeds using electric power. Xenon gas is the most common choice. The atoms are ionized, stripped of electrons, and then expelled through an electric field at velocities far greater than chemical exhaust. Although thrust is low, typically measured in millinewtons, the specific impulse is many times higher than conventional rockets. In practical terms, each kilogram of xenon yields far more usable change in velocity than a kilogram of hydrazine or liquid hydrogen. Ion engines, therefore, do not strive to push a spacecraft quickly at launch. They aim to add velocity gradually, accumulating speed over long periods of operation. This slow accumulation is well suited to deep space, where the absence of atmospheric drag allows tiny impulses to remain effective. Each thrust cycle alters the spacecraft's momentum slightly. Over thousands of hours, these increments compound, eventually producing velocities that chemical rockets cannot achieve without burning untenable amounts of fuel. Missions such as NASA's Dawn spacecraft demonstrated this pattern clearly. Dawn spent months spiraling outward, reshaping its orbit using steady ion thrust to move between the asteroid Vesta and the dwarf planet Ceres. The craft did not rely on singular burns. Instead, it rode a continuous stream of electrically accelerated particles, adjusting its trajectory in a controlled and predictable manner. Electric propulsion changes the relationship between propellant and time. Because ion engines expel exhaust at such high velocity, the spacecraft needs far less reaction mass to generate the same change in momentum. This efficiency permits extended thrust periods without carrying prohibitive propellant reserves. The limiting factor shifts from onboard fuel to available electrical power. Solar arrays or nuclear sources must supply energy to ionization chambers and acceleration grids. If power wanes due to distance from the sun, degradation, or shadowed geometry, the thrust weakens. Performance becomes a function of energy availability rather than internal storage capacity. This dependency defines the operational envelope of ion-based missions. The slow nature of ion propulsion also allows continuous trajectory refinement. Instead of setting an orbit and coasting, a spacecraft can subtly adjust its path over time. These modifications can be planned in advance or executed in response to deviations measured during flight. The strategic benefit lies in flexibility. Rather than waiting for concentrated burns, engineers can command gradual course shifts that accumulate smoothly. The spacecraft becomes less sensitive to the timing of corrections and more capable of fine-tuning its approach. The method imposes no sudden mechanical stresses and does not require large structural margins. It distributes energy evenly across months. However, ion propulsion does not eliminate constraints imposed by the Sun's gravity. It still operates within transfer geometries and orbital mechanics. Continuous thrust enables trajectories that deviate from perfect ellipses, but the spacecraft cannot ignore celestial influence. In many cases, ion missions still launch during favorable windows and then use sustained thrust to tighten arrival schedules or minimize insertion burns at the destination. The advantage is not raw speed. It is controlled acceleration that reshapes time without demanding enormous fuel mass. Ion systems are not universally appropriate. They provide insufficient thrust for launch, ascent, or rapid maneuvering near large bodies. Their operational strength lies in the cruise phase, far from dense atmospheres and deep gravitational wells. Power systems must be reliable and redundant because thrust stops entirely if electricity falters. Engineers must account for degradation in solar arrays, potential dust accumulation, and radiation effects on power electronics. Every hour of thrust depends on persistent hardware function, and every hour contributes to the cumulative performance. Ion propulsion illustrates that slow motion can be strategically superior. It trades intensity for persistence, using the physics of momentum to outlast brute force. With this approach understood, attention turns to how spacecraft behave when they finally reach the Martian system and must convert accumulated speed into a controlled encounter. Every kilogram carried changes everything. Fuel itself weighs something, equipment weighs something, safety weighs something. The more you bring, the harder you must push, and the longer the trip becomes. Mars is not only far away, it resists being approached by anything heavy. Spacecraft design begins with mass budgets. Every component, from propellant tanks to scientific instruments, occupies a share of limited capacity. Engineers express these balances in terms of dry mass, payload mass, and propellant mass. Dry mass includes structure, computers, power systems, and life support in crude designs. Payload mass includes cargo, landers, or scientific equipment. Propellant mass represents the fuel that will be expended to place a vehicle into orbit, perform burns, and enter transfer trajectories. The ratios between these categories determine mission feasibility. Increasing one category requires reducing another or expanding the launch system. The trade-offs are unforgiving because the cost of lifting mass escalates rapidly with scale. This escalation arises from the rocket equation. A rocket accelerates by expelling mass at high velocity. To achieve greater change in speed, or delta V, more propellant must be added. But added propellant increases the total mass that must be accelerated. The equation becomes recursive. Extra fuel requires additional structural mass to contain it, and additional structural mass requires even more fuel to accelerate. The problem is not poor engineering. It is mathematical. The rocket equation places exponential penalties on attempts to increase performance by simply adding more fuel. Early stages of launch vehicles often exist solely to provide the energy required to place later stages and payloads into orbit. These stages are discarded once their fuel is spent, demonstrating how quickly mass becomes a liability. Interplanetary missions magnify these effects. A spacecraft traveling to Mars must perform multiple major maneuvers: launch into Earth orbit, escape Earth's gravity well, enter a solar transfer path, correct its course during cruise, and adjust velocity or perform insertion when arriving. Each maneuver subtracts from the available fuel. Carrying enough propellant to perform all burns at high energy would require prohibitively large tanks and stronger launch vehicles. Crewed spacecraft compound the problem. Water, oxygen, food, radiation shielding, and environmental systems all contribute to mass. Each kilogram transported to space increases launch demands and reduces margin for additional fuel or scientific payload. Reducing mass, therefore, becomes a priority. Designers seek lightweight structural materials, efficient power systems, and compact electronics. Habitats for crewed missions are analyzed to minimize unnecessary volume. Consumables are packaged tightly and often regenerated or recycled. Even the geometry of tanks and solar arrays is optimized to maintain mass while preserving functionality. These decisions do not reflect aesthetic preference. They serve the underlying mathematics of propulsion. Small savings in mass propagate through the mission architecture, reducing total fuel requirements and expanding feasible launch options. Mass considerations extend beyond launch. During the cruise phase, spacecraft must maintain stability, orientation, and thermal balance. Larger vehicles require more momentum for rotation and more robust systems to manage internal heat. Additional radiators, control thrusters, and support hardware add still more mass. These additions can be minimal individually, but their cumulative impact affects mission performance. The mass carried into deep space influences the complexity of every maneuver, from minor corrections to terminal burns near Mars. Landing on Mars introduces another layer of mass sensitivity. A vehicle entering the Martian atmosphere must decelerate, using either aerodynamic resistance or propulsion. Heavier craft require stronger heat shields, larger parachutes, or increased fuel for powered descent. Each of these systems adds weight that was carried from Earth. The landing system is not isolated at the end of the mission. It is part of a chain that begins at launch. Crew capsules, cargo landers, and return vehicles must all balance entry systems with ascent systems, storage capacity, and reusability goals. Even when partial solutions exist, mass determines whether they can be implemented. Understanding fuel and mass clarifies why missions to Mars are engineered around constraints rather than ambition. Mass dictates propulsion choices, timing strategies, and hardware design. Once mass is managed, the next question becomes how that mass behaves when crossing the Martian boundary and preparing to slow into the planet's gravitational embrace. Look at the numbers. Tens of millions of kilometers shrink to abstractions that the mind strains to hold. Maps help, but they do not convey the emptiness between points. Your spacecraft travels for months simply because space is large enough to demand it. This is the scale of planetary travel. Distances in the solar system are not measured in familiar units. They are expressed in millions of kilometers because lesser scales fail to capture the span between worlds. Earth and Mars are neighbors by astronomical standards, yet the separation between them can dwarf any journey conducted on Earth. Even at their closest approach, the two planets sit far enough apart that radio signals require minutes to travel between them. At greater separations, the light time delay stretches to 20 minutes or more, rendering real-time communication impossible. These distances are not philosophical curiosities. They define navigation, propulsion, and mission architecture. It must follow orbits shaped by gravity and time. Human perception lacks the sensory tools to understand such separations naturally. On Earth, depth is conveyed by parallax, atmospheric haze, and the size of familiar objects. In space, none of those cues exist. the night sky compresses the three-dimensional structure of the solar system into a flat backdrop. Mars appears only as a dot, no matter how near or far it lies. Without calculation, distance is indistinguishable from brightness or motion. Astronomers therefore model planetary positions using coordinates, orbital ephemerides, and geometry rather than visual judgment. Spacecraft navigation builds on these models, referencing distance not as a physical space to cross, but as a schedule of motion through gravitational fields. Distances also impose velocity constraints. When a spacecraft leaves Earth, it carries Earth's orbital speed and receives additional velocity from its launch sequence. That initial momentum allows it to move outward, but only incrementally. The Sun's gravity slows the outward motion as the spacecraft climbs away from its initial orbit. Even if engines could burn continuously, velocity still accumulates against a gravitational gradient. Should propulsion fail, the spacecraft continues along a predictable path. It does not stop. It continues on an orbit determined by its last successful burn. The emptiness between planets does not offer support or resistance, it provides continuity. Motion continues unless energy is supplied to reshape it. Energy, in turn, is limited by mass. The propellant required to accelerate continuously across tens of millions of kilometers would be immense. Instead of brute force, missions rely on celestial mechanics. The spacecraft follows a curved transfer trajectory that replaces constant thrust with gravitational conservation. This approach uses distance as a structural element, not an obstacle. The spacecraft's path stretches outward slowly, trading mass efficiency for travel time. Months of motion are not wasted intervals. They are the natural consequence of crossing heliocentric space without exhausting fuel reserves. Cosmic distance also influences spacecraft operations. Navigation signals must be transmitted and returned through enormous spans. Ground networks send commands, then wait for replies. Each exchange is separated by minutes, complicating troubleshooting and reducing responsiveness. Spacecraft autonomy bridges these delays. Guidance systems track stars, estimate velocity from Doppler shifts, and correct orientation with small impulses. These systems function continuously because communication cannot function instantly. The gap between planets shapes engineering choices as much as physics shapes flight paths. Even robotic explorers reflect the implications of distance. Mars rovers receive driving commands in batches, then execute sequences while mission teams wait. Orbital satellites transmit compressed data because bandwidth over interplanetary links is limited. Every operational detail bends to the separation between worlds. The gulf is not merely spatial, it is procedural. Understanding distance allows missions to function reliably despite it. Cosmic distances remind mission planners that speed, fuel, and trajectory exist within a framework set by scale. The voyage to Mars is not prolonged because spacecraft are weak, but because the solar system is large. Recognizing this scale provides context for the next step. When the spacecraft reaches Mars, it must decelerate and adapt to the planet's immediate environment. As you glide farther from Earth, conversation slows. A message sent from home requires minutes to arrive. You respond, and minutes pass again. You do not feel this delay. It accumulates silently. Distance turns seconds into minutes, and minutes into patience. The speed of light is immense on human scales, yet modest across interplanetary distances. In a vacuum, electromagnetic signals travel nearly 300,000 kilometers per second. This value seems instantaneous when transmitting across continents or to satellites orbiting Earth. But as the separation between planets grows, the finite nature of light becomes measurable. Earth and Mars can be separated by tens of millions of kilometers, even at their closest approach. During these periods, a one-way signal often takes several minutes to reach its destination. When the planets drift to opposite sides of the Sun, the delay stretches beyond 20 minutes. Every command, every piece of telemetry, is therefore framed by intervals that cannot be compressed or negotiated away. Mission operations adapt to this cadence. Engineers send sequences of instructions rather than single commands. Spacecraft receive packets outlining multiple actions, then execute them autonomously. During a rover's drive, operators do not steer turn by turn. They define waypoints, speeds, and safety limits. The rover interprets local terrain with sensors, avoids hazards when possible, and then reports its progress after completing the assigned task. These cycles may occupy an entire Martian day because the signal must travel outward, be acknowledged, and then travel back. The communication pattern is not casual, it is structural. Navigation systems compensate in similar fashion. Spacecraft cannot be maneuvered manually in response to real-time readings. They carry star trackers, gyroscopes, accelerometers, and ranging instruments that continuously monitor their own motion. These sensors allow onboard computers to estimate position and velocity without waiting for ground direction. When course corrections are required, engineers send burn parameters, not moment-to-moment steering. The process repeats with an awareness of the unavoidable delay. Latency transforms outages into periods of uncertainty. During planetary conjunctions, solar plasma interferes with radio waves, distorting or blocking communication. Although spacecraft are not physically endangered by the sun's presence, message clarity deteriorates. Operators adopt conservative strategies, placing spacecraft into safe configurations and limiting activity until geometry improves. Even in the absence of conjunction, temporary communication gaps can arise from tracking station handovers or antenna maintenance. Because corrections require time to propagate, operational safety depends on robust autonomous routines that prevent spacecraft from drifting or making uncontrolled adjustments while awaiting instructions. Data transmission also reflects distance. Signals weaken as they spread outward, forcing communication systems to use narrow bandwidths and specialized encoding. Instruments on board Mars orbiters and landers gather large amounts of information, but downlink rates remain constrained. High-gain antennas and relay spacecraft mitigate these limits, yet they cannot eliminate them. Scientific operations are paced by the capacity of interplanetary communication links rather than the speed at which instruments collect data. Mission designers schedule observations around anticipated bandwidth windows, planning days or weeks ahead. For human missions, latency becomes psychological as well as operational. Astronauts would not converse with Earth in real time. Questions asked during transit receive replies after long intervals. Emergency responses must rely on onboard procedures and trained crews rather than immediate ground intervention. The relationship between flight controllers and crews becomes episodic rather than continuous. Mission planning must therefore incorporate independence, medical capacity, maintenance protocols, and decision-making authority, knowing that communication will lag. The communication delay does not signify technological inadequacy. It is the predictable result of scale and physics. Signals cannot outrun light, and planets do not pause to accommodate human expectations. Systems must be designed around these facts rather than attempting to bypass them. Interplanetary missions succeed because they assume latency from the start and build operational architectures that function within it. Communication delay illustrates how distance shapes not only travel, but interaction. Once a spacecraft reaches Mars, another delay awaits. Movement must be reduced, and that reduction determines how entry, descent, and capture are performed. Halfway to Mars is not a midpoint of effort. It is simply a point in space where your outbound velocity continues to build. You have not yet arrived, but you cannot turn back efficiently. The journey becomes self-committing long before arrival. Mid-course navigation is a process of maintaining trajectory rather than redefining it. Once a spacecraft has departed Earth, it is placed on an orbital track around the Sun, not a linear path across emptiness. That orbit is determined by the initial burn, the spacecraft's mass, and the gravitational environment it travels through. Corrective maneuvers are used not to move the spacecraft toward Mars in a direct sense, but to refine its intersection with Mars's future position. Even when the spacecraft is tens of millions of kilometers from both planets, it does not float freely. It remains within a predictable gravitational arc set by its last propulsion event. Navigation teams track that arc constantly, using telemetry and modeling to ensure the vehicle remains aligned with its intended arrival corridor. Midpoint distance does not correspond to midpoint velocity or midpoint effort. The spacecraft typically travels fastest near the Sun, where gravitational potential is lowest, and slows as it climbs outward. If plotted on a graph of distance versus velocity, the profile resembles a gradual rise toward Mars's orbit rather than a symmetric climb and descent. The halfway mark is therefore an arbitrary spatial milestone. It does not reflect the remaining energy budget or the difficulty of course changes. Attempts to reverse direction at this stage would require enormous delta V, because the spacecraft must not only negate its forward velocity, but also re-enter Earth's gravity well. The cost of reversal far exceeds the energy needed to remain on course. Course corrections during this phase are planned to be minimal. Mission designers prefer early adjustments because they yield large, long-term effects. A small change in velocity, applied soon after departure, can reposition the spacecraft by thousands of kilometers months later. Later corrections are less efficient because they occur when the spacecraft is already distant from its origin and traveling along a more rigid orbital path. Mid-course burns are therefore scheduled strategically. Teams analyze expected deviations using tracking information from ground networks, typically the Deep Space Network, and determine where a short pulse of thrust will produce the most useful geometric shift. Navigation involves multiple sensing modalities. Radio ranging measures distance using signal travel time. Doppler tracking derives velocity from shifts in frequency. These data streams form a trajectory solution that describes not only position but motion relative to celestial bodies. Spacecraft also carry onboard instruments such as star trackers and inertial measurement units, which allow them to maintain orientation when communication is intermittent. The integration of ground measurements and onboard sensing prevents drift from accumulating unchecked. Navigation is continuous in analysis, even if infrequent in action. Momentum plays a central role in mid-course behavior. Once a spacecraft collects outbound velocity from its initial burn, it continues along its heliocentric orbit unless acted upon. Gravity shapes that motion but does not halt it. Even if engines were disabled entirely, the spacecraft would still intersect Mars's orbit at a later time, though not necessarily at the correct moment. This feature protects missions from single points of failure. Navigation systems may fail temporarily, but orbital mechanics maintain motion reliably. The spacecraft cannot stop in deep space because there is no medium to slow it. It coasts forward along the dictates of its last commanded trajectory. The psychological idea of turning back misrepresents interplanetary reality. Returning is not as simple as flipping orientation. It demands substantial acceleration, equal to or greater than the energy already expended. The spacecraft would need to reverse velocity, descend toward the Sun, and re-establish an Earth-bound orbit. Such maneuvers are prohibitively expensive unless they are incorporated into mission planning from the start. The notion of a point of no return is not dramatic. It is practical. The commitment to the path occurs as soon as the departure burn is complete and the spacecraft begins its solar journey. The midway phase reinforces how interplanetary travel is defined by momentum rather than intention. Once velocity and geometry align, the mission continues forward because physics encourages continuation. That momentum must eventually be countered, which leads to the next stage, how the spacecraft slows and prepares to transition from interplanetary space into the influence of Mars. Tiny deviations compound. A fraction of a degree at launch becomes thousands of kilometers months later. Mid-course corrections are not failures, they are the natural consequence of orbital flight. Precision over time is the only path to intersection. Interplanetary navigation is an exercise in continuous refinement. From the moment a spacecraft leaves Earth, its trajectory is influenced by small forces that accumulate over time. The initial burn establishes the general path, but the burn cannot be perfect. Structural tolerances, engine performance variation, and atmospheric effects during ascent introduce minute errors in velocity and direction. Once the spacecraft is in heliocentric orbit, these errors are carried forward along its trajectory. Because travel spans tens of millions of kilometers, even a minute discrepancy at launch can translate into a vast positional offset by the time the spacecraft reaches Mars's orbit. A trajectory that appears accurate early in flight may diverge substantially months later, if not monitored and corrected. Course correction maneuvers address this divergence. They typically occur at predetermined checkpoints during cruise. Mission teams use tracking data to determine how far the spacecraft has drifted from its predicted arc, and then calculate a burn to realign its motion. These burns are short, often lasting seconds or minutes. Because the required changes in velocity are small, they adjust the spacecraft's direction or timing rather than altering its mission objective. The corrections are scheduled strategically to minimize fuel consumption. An early course adjustment produces larger downstream benefits because the spacecraft has more time to propagate the change along the remainder of its journey. A late correction must work against accumulated error and therefore expends more propellant. Tracking systems enable the detection of small deviations. The Deep Space Network measures distance by timing radio signals and derives velocity from Doppler shifts in their frequency. These observations are integrated into a trajectory solution that compares expected motion with actual motion. If the difference grows beyond acceptable margins, a correction sequence is programmed. During this process, engineers consider spacecraft orientation, remaining fuel, and the effect of the burn on expected arrival geometry. They do not view deviation as malfunction. They treat it as a predictable outcome of imperfect inputs, operating in a dynamic environment. The timing of corrections is as important as their magnitude. Orbital mechanics grant leverage near perihelion, where the spacecraft moves fastest relative to the Sunday. A small burn at high velocity produces greater overall trajectory change than the same burn at lower velocity. Mission planners, therefore, seek windows where adjustments produce maximum effect. When available, these opportunities reduce propellant expenditure and preserve reserves for arrival and insertion burns. Corrections may also be distributed across several smaller maneuvers to avoid stressing thrusters or introducing abrupt directional changes. A spacecraft's design accommodates these adjustments. Thruster arrays are positioned to impart force evenly, preventing unwanted rotation. Reaction control systems handle orientation, while dedicated propulsion units provide tiny changes in momentum. Navigation computers store burn programs and execute them autonomously, often without real-time input from Earth. The process is methodical rather than dramatic. The spacecraft monitors its own position, applies thrust, and then sends confirmation telemetry. Whether in the early weeks of flight or the final months, the goal remains the same: maintain the planned intersection with Mars's future location. Mid-course corrections continue until mission teams are confident that the spacecraft will arrive within required boundaries. As the craft approaches Mars, desired precision increases. Small angular errors translate into major consequences when the target is no longer an orbit tens of millions of kilometers wide, but a planetary sphere or a specified entry corridor through atmosphere. Corrections refine trajectory from a broad interplanetary path into a narrow arrival geometry. Every adjustment narrows uncertainty, improving the likelihood of a successful encounter. Course corrections illustrate that interplanetary navigation is a process, not a single decision executed at launch. A spacecraft does not travel untouched. It is shepherded. Once its path is refined and arrival draws near, attention shifts to managing the energy it carries and preparing to slow it into Mars's gravitational domain. Approaching Mars is not about braking at the finish line. You synchronize motion with an entire world. Your arrival must coincide with the planet's orbital position, rotational timing, and gravitational environment. Landing begins long before the spacecraft ever sees the ground. Arrival windows emerge from the same orbital constraints that govern departures. A spacecraft approaching Mars follows a predetermined heliocentric path, and its arrival occurs at a point where that path intersects the planet's orbit. The spacecraft does not meet Mars in open space by chance. It meets Mars because its trajectory was designed to cross the orbit at the correct moment. This moment is not arbitrary. The planet has its own velocity, its own direction, and its own gravitational pull. If a spacecraft reaches Mars too early, the planet has not yet arrived at the rendezvous point. If it arrives too late, Mars has passed, forcing additional burns or resulting in a missed encounter. Arrival timing therefore controls the feasibility of insertion maneuvers and dictates whether the mission transitions smoothly into the Martian system. The arrival window narrows more than the departure window because the spacecraft's velocity relative to Mars becomes the dominant variable. Interplanetary cruise reduces flexibility. A mission in transit carries momentum, accumulated over months. Once inbound, that momentum cannot be removed easily. Increasing or decreasing arrival speed months before encounter requires large changes in delta V, consuming the limited fuel reserves preserved for insertion. As a result, planners determine allowable arrival rhythms before launch. They calculate target velocities and orbital geometry so that only moderate burns are needed to establish orbit or begin entry. These parameters are maintained through mid-course corrections. The spacecraft adjusts its path during the long cruise so that its arrival conditions match predetermined constraints. Mars's rotation introduces a second layer. Surface landing is not simply a matter of descending toward the planet. The location beneath the spacecraft changes continuously as the planet spins. A lander targeting a specific site must be timed to reach the atmosphere when that location passes under the arrival corridor. If the timing is incorrect, the lander may encounter different terrain or atmospheric conditions. Orbiters also rely on rotation. They may target insertion times that align with desired lighting or seasonal monitoring. These constraints layer onto orbital geometry, tightening acceptable windows further. Arrival becomes a combined alignment of space and time. Atmospheric properties add another constraint. Mars has a thin but complex atmosphere, capable of generating variations in density, wind, and temperature. Entry windows account for these variations to reduce uncertainty during descent. Landing systems, parachutes, heat shields, retropropulsive engines, or skycrane mechanisms operate within specific velocity and altitude profiles. Deviations from expected atmospheric behavior can alter how quickly the spacecraft decelerates or how it deploys descent hardware. Arrival during dust storm seasons may require higher redundancy or conservative entry paths. Though these seasonal considerations do not dictate orbital geometry, they influence mission planners, who may adjust arrival dates modestly to reduce risk. Orbiters face their own arrival constraints. To join Mars's gravitational domain, they must shed energy without risking escape or collision. Aerobraking, propulsion burns, and capture trajectories rely on a precise balance between spacecraft velocity and planetary mass. If arrival occurs outside the intended window, these procedures may become unsafe or inefficient. The difference between a manageable insertion burn and a high-energy emergency burn can be traced back to arrival timing. Engineers choose margins that protect against error, but geometry still dictates the safe envelope for deceleration. Arrival windows are also shaped by planetary satellites and other spacecraft. Mars's system includes Phobos and Deimos, whose orbital paths must be considered. Though their influence is relatively small, arrival trajectories cannot intersect their motion. Additionally, existing orbiters coordinate radio link timing and relay schedules. A mission may target insertion when communication infrastructure is available, enabling tracking and early diagnostics. These operational concerns are not secondary. They ensure that spacecraft can confirm health and performance in the first moments of Martian capture. Understanding arrival windows demonstrates that mission planning does not end at launch. It extends through cruise and into the final phase of approach, in which timing determines how and whether a spacecraft becomes bound to Mars. Once timing is set, the next step examines how this arrival energy is reduced, allowing the spacecraft to pivot from interplanetary motion into orbit or descent. Mars has an atmosphere, but it is thin. Too thin to lift you gently, too thick to ignore. Your spacecraft must absorb heat, bleed energy, and decelerate with care. The final leg of the journey is quiet in space, then violent in chemistry. Atmospheric entry at Mars is an engineering negotiation with physics. The planet's atmosphere is composed primarily of carbon dioxide and is much less dense than Earth's. At the surface, its pressure is less than 1% of that on Earth. This thin envelope cannot provide the robust aerodynamic braking that terrestrial entry vehicles rely on. Yet it is dense enough to generate frictional heating when a spacecraft arrives at interplanetary velocities. The challenge lies in reducing energy without overwhelming the thermal protection system or exhausting fuel stores. Instead of a simple descent, atmospheric entry becomes a controlled conversion of kinetic energy into heat, managed through carefully engineered hardware. The first line of defense is the heat shield. During entry, the shield faces the direction of travel and absorbs the energy generated by compression of the Martian atmosphere. The heating process is not primarily frictional. It is caused by the gas ahead of the spacecraft being compressed to extreme temperatures. When molecules of carbon dioxide collide and slow abruptly, they emit heat, transferring it onto the shield. The shield's material, often an ablative composite charred or vaporized, intentionally to remove thermal energy. This controlled erosion keeps the spacecraft beneath safe temperature thresholds. The shield is designed to withstand intense thermal loads for a short period, after which aerodynamic forces become manageable. Deceleration must follow a narrow corridor. Too shallow an entry angle, and the spacecraft may skim across the atmosphere without slowing, failing to capture. Too steep, and the vehicle plunges downward too quickly, subjecting itself to excessive forces and heat. The entry profile is determined months in advance, based on predicted atmospheric conditions, spacecraft mass, and velocity. During the approach, navigation teams make small corrections to ensure the vehicle arrives within this corridor. Once entry begins, real-time control is minimal. The spacecraft follows the predetermined trajectory and relies on its aerodynamic surfaces to generate stability. Mars's thin air requires alternative braking methods once the initial heating phase concludes. Parachutes are traditionally deployed at supersonic speeds. They slow the descent but cannot provide gentle landing authority. The parachutes are large relative to spacecraft mass and must be deployed at specific dynamic pressures to avoid structural failure. Even then, they produce limited drag. Landing systems must take over after parachute deployment. Some missions carry retropropulsive engines that ignite to cancel remaining velocity. Others use airbag systems or sky cranes to deliver payloads to the surface. All approaches reflect the same principle. Entry converts most energy to heat, but not all. Atmospheric variability complicates precision. Mars experiences dust storms that alter density and temperature profiles. These storms can extend globally, reducing solar illumination and changing aerodynamic behavior. Entry models must include possible ranges of density fluctuations. Spacecraft may be fitted with sensors that measure atmospheric conditions in real time, adjusting burn timing or descent rate accordingly. This strategy improves reliability but does not eliminate uncertainty. Engineers design margins into each phase to protect against deviations from expected conditions. Orbiters also encounter entry limitations. Rather than descending directly to the surface, they perform insertion burns to capture into orbit. Some missions use aerobraking to reduce orbital altitude gradually. Instead of burning fuel, they dip into the upper atmosphere repeatedly, allowing drag to reduce velocity across hundreds of passes. Each pass produces minimal heating, spreading thermal stress over time. The method is fuel-efficient but slow, taking months to complete. The thinness of the Martian atmosphere makes this process viable. Thicker atmospheres would produce destructive heating at comparable speeds. The complexity of atmospheric entry illustrates how interplanetary missions must adapt to the environments they encounter. Spacecraft cannot rely on a single mechanism to slow themselves. They combine thermal protection, aerodynamics, parachutes, and propulsion in layered sequences that respect Mars's unique atmospheric profile. Entry is a transformation in motion, performed on precise schedules and governed by fundamental physics. With the atmosphere managed, the next phase considers the alternative route, a spacecraft that does not descend into air, but instead remains in orbit to continue its mission. You descend into a gravity field weaker than Earth's, but strong enough to matter. Parachutes unfurl, engines fire, and velocity falls in measured stages. The planet accepts you gradually. The last kilometers demand more planning than the first millions. Surface descent at Mars is governed by layered braking systems designed to operate sequentially, each compensating for the limitations of the one before it. The planet's gravity is roughly 38% of Earth's, which reduces terminal velocities in the absence of atmosphere, but the thin Martian air offers limited aerodynamic resistance. Spacecraft arriving from interplanetary trajectories typically approach the upper atmosphere at several kilometers per second. No single method can slow that momentum to a safe landing speed. Instead, descent is divided into carefully choreographed phases that collectively dissipate energy. Each step is tested, modeled, and executed with tolerances refined over decades of robotic exploration. The descent sequence begins once the heat shield completes its role in atmospheric entry. When dynamic pressure drops to a predictable level, a parachute is deployed. Mars parachutes are large relative to spacecraft mass because they must compensate for reduced drag. Designs such as disc gap band chutes have proven reliable at supersonic speeds. Their function is not to bring the spacecraft to a halt, but to reduce velocity from hypersonic to subsonic regimes. Deployment occurs automatically, triggered by altitude, inertial data, or aerodynamic thresholds. Timing is critical. If the chute opens when the air is too thin, effectiveness falls. If it opens when velocity is too high, structural stress risks tearing the canopy. These margins are engineered into the descent plan long before arrival. As the parachute slows the spacecraft, the lander separates from its back shell and exposes additional hardware. Radar altimeters and inertial sensors establish actual descent rate and altitude. The remaining kinetic energy must be addressed using engines, airbags, or descent cranes. Retropropulsive engines offer controlled deceleration by pushing against the direction of travel. They allow the spacecraft to tune its descent profile, matching thrust to altitude and speed. This capability enables precision landing when targeted sites require accuracy. However, propulsion increases complexity and fuel requirements, and exhaust can disturb surface regolith, affecting sensors and stability. Engineers weigh these outcomes against mission goals. Airbag systems, used in earlier Mars missions, take a different approach. Instead of hovering or throttling engines just above the surface, a lander is enclosed within protective bladders. After chute-assisted deceleration, the lander is cut free and allowed to impact the ground at survivable speeds. The airbags absorb shock, bouncing and rolling until energy dissipates. This method minimizes propellant but limits payload mass and surface stability. More complex or delicate scientific payloads benefit from descent cranes or propulsive landings. The sky crane approach, used for rovers such as Curiosity and Perseverance, decouples the lander from its descent stage during final meters. Cables lower the rover gently, while engines maintain hover. After touchdown, the descent stage flies away to avoid collision. Sensors guide all descent architectures. Radar, laser altimetry, and onboard navigation systems measure terrain and velocity. In some cases, onboard imaging maps the ground in real time, enabling hazard avoidance. Terrain relative navigation compares camera data to stored maps, adjusting trajectory to avoid boulders or canyons. The spacecraft must make decisions autonomously because latency prevents ground intervention. These systems reduce risk, especially when landing in scientifically interesting but uneven regions. Surface descent requires vehicles to operate in varying atmospheric densities and temperatures. Design must anticipate dust, turbulence, and the uneven thermal environment of Mars's lower atmosphere. Thrusters must remain responsive. Sensors must remain unobstructed, and insulation must protect electronics from rapid temperature changes. The engineering effort does not focus on spectacle. It focuses on reliability under well-understood constraints. Each descent profile is tailored to mission mass, target site, and environmental expectations. Surface arrival completes the high-energy phase of a Mars mission. Once the spacecraft touches down, the The complexities shift from flight to operation. Instruments must deploy, power systems must stabilize, and communication links must re-establish. With descent understood, the next stage examines how orbiters, unlike landers, do not touch the surface at all, but instead remain aloft to continue scientific or logistical roles. Machines tolerate months in transit, with indifference. Humans carry metabolism, radiation exposure, supplies, routines. The clock becomes biological rather than mechanical. Travel time is about survival of systems, not just arrival of hardware. Human missions to Mars transform interplanetary travel into a question of physiology. Spacecraft are not simply platforms for instruments, they become habitats. Astronauts must remain healthy, hydrated, nourished, and psychologically stable during months-long transit. The basic needs of the body introduce continuous consumption of limited resources. Water, oxygen, and food must be stored or regenerated throughout the journey. A 6-month voyage requires less than one lasting 8 months, and any contingency reserve adds more. Mission planners evaluate how long crews can remain safely in transit and how margins influence life support architecture. The timeline becomes a variable with biological cost. Microgravity produces degradation in muscle, bone, and cardiovascular function. Without sustained loading, the body begins to shed tissue. Astronauts aboard the International Space Station manage these effects through daily exercise routines. Their experience informs expectations for Mars missions, but the environment differs. A Mars transfer vehicle offers less volume and fewer exercise options. Hardware must be chosen for reliability and mass efficiency, capable of operating continuously in near-vacuum conditions. Crew adherence becomes routine rather than optional. The longer the journey, the greater the physiological decline that must be countered through exercise, nutrition, and monitoring. Radiation poses another time-dependent hazard. Earth's magnetosphere protects orbiting astronauts, but interplanetary space does not. Solar energetic particles and galactic cosmic rays bombard spacecraft interiors. Shielding reduces exposure, but shielding adds mass. Designers must choose between heavier structures and more vulnerable crews. Active dosimetry tracks exposure and helps manage risk, but it cannot eliminate it. Time amplifies radiation accumulation. A shorter voyage yields lower total dose, while longer transfers demand thicker shielding or strict operational limits. Transit time therefore influences vehicle layout, material selection, and mission duration caps. Life support systems evolve under these constraints. Closed-loop architecture reclaims air and water, reducing the mass of stored consumables. Carbon dioxide scrubbers, humidity condensers, and filtration units must function continuously. Redundancy is essential, as failure modes cannot be resolved by immediate resupply. Each subsystem requires power, maintenance, and crew intervention. The reliability of these systems shapes acceptable mission lengths. More time in transit increases the probability of hardware degradation, microleaks, or contamination. Engineers therefore balance mission profiles to limit cumulative failure risk. Psychological considerations also scale with duration. Isolation, confinement, and delayed communication create conditions unlike any terrestrial environment. Crews must manage stress, morale, and interpersonal dynamics without real-time conversation with ground teams. Behavioral support becomes programmatic rather than improvised. Transit length determines the cadence of scheduled interactions, recreation, and workload. Even simple events, such as message exchanges with Earth, stretch into asynchronous dialogues. Mission planners design schedules that reduce monotony and maintain cognitive engagement. Acknowledging that boredom is not trivial, it is operational. Medical autonomy increases as distance grows. Minor injuries or illnesses cannot wait for remote guidance. Crews must diagnose and treat problems directly, using stored pharmaceuticals, onboard diagnostics, and procedural training. Chronic conditions, allergic reactions, or infection carry elevated risk when treatment windows are extended by communication latency. The longer the voyage, the greater the chance of encountering such situations. Mission designers consider crew selection carefully, preferring individuals with strong medical resilience and cross-disciplinary skills. Transit time influences crew composition as surely as it influences vehicle design. Human timelines reshuffle priorities. A trajectory chosen for fuel efficiency may be inappropriate if it increases exposure or reduces mission safety margins. Faster transfers reduce risk in some domains while increasing it in others. Mission planners weigh radiation, consumables, exercise capacity, and psychological stability against mass constraints and propulsion options. These evaluations turn transit duration into a variable with cascading implications for hardware, training, and logistics. The distance to Mars becomes a function not only of kilometers, but of biological endurance. Understanding human timelines reveals why travel to Mars cannot be considered in purely mechanical terms. Spacecraft might tolerate months of cruise with little consequence, but crews transform those months into operational demands. With transit accounted for, attention shifts to what awaits after arrival. Habitation on the Martian surface and the rhythms that follow landing. After all the geometry, patience, and propulsion, you look back at the original question. How long does it take to reach Mars? The answer is not a single number. It is a range defined by physics, policy, and probability. You begin to see why every mission's timeline feels unique. When mission planners discuss transit duration, they do not speak in absolutes. They describe windows, trajectories, and operational constraints. The most fuel-efficient method, the Hohmann transfer, produces travel times typically between 6 and 8 months. This duration reflects the spacecraft's slower outward climb through the Sun's gravitational field and the limited thrust employed during cruise. Faster methods exist, but they demand more energy at launch or during the journey. The energetic cost may be acceptable for robotic missions carrying modest payloads, yet prohibitive for crewed vehicles requiring life support systems, radiation shielding, and redundancy. The practical question becomes less how fast and more how much mass and risk are tolerable. Historical missions illustrate the variability. Some spacecraft launched during optimal windows have arrived in the lower half of the typical range by following carefully tuned trajectories. Others, using high-energy transfers, have reached Mars more quickly, but at the expense of fuel and payload capacity. Conversely, missions that rely on gravity, assists, or extended cruise periods may reach Mars later, trading speed for resource efficiency. These examples show that time to Mars is not determined by distance alone. It is shaped by the method of travel and the mission's objectives. Human missions change the calculus further. A crewed vehicle might avoid extreme accelerations that expose astronauts to unnecessary forces. It may choose gentler transfer arcs to limit radiation dose. Even if they lengthen transit, mission designers also consider psychological and logistical factors. Exercise regimens, consumable stores, medical support, and communication delays. Faster trajectories reduce time spent in microgravity and radiation environments, but require additional fuel and stronger engines. These trade-offs cannot be evaluated independently. They are interconnected, and each decision influences the next. Policy and programmatic decisions introduce additional variability. Launch schedules are influenced by funding cycles, vehicle readiness, and national priorities. Delays push missions into less optimal windows, increasing fuel demands or shifting descent conditions. International partnerships can alter cadence, as multiple agencies coordinate infrastructure or relay systems. Mission design becomes a negotiation not only with celestial mechanics, but with institutions that operate within fiscal and technological boundaries. A spacecraft may be physically capable of departing sooner, yet still wait years to align with hardware availability or political consensus. The arrival phase completes the time equation. The spacecraft's approach speed determines how much braking is required, whether by atmospheric entry, orbit insertion burns, or aerobraking. These procedures demand fuel, heat shielding, or long operational timelines. A mission that arrives slightly earlier or later than planned might face different environmental or seasonal conditions, prompting the use of more cautious descent profiles. The time spent between atmospheric entry and surface landing can vary by hours or by months, depending on whether the vehicle lands directly or captures into orbit first. Arrival is not a single moment. It is a process. For most Mars missions, a commonly cited travel envelope of 6 to 9 months reflects a balance between practicality and physics. Within that range, variations are normal rather than exceptional. A launch at the center of a window may shorten cruise, while a launch at its edges may extend it. High-energy approaches compress the journey, but transform mass requirements. Ion propulsion may lengthen initial travel, but reduce insertion fuel. No number is universally correct, because no mission shares identical conditions, geometry, or intent. The practical answer, then, is neither evasive nor vague. It is conditional. Travel time depends on trajectory choice, propulsion type, payload mass, launch timing, and mission goals. Mars is always reachable, but never on identical terms. Understanding that nuance provides closure to the question. To reach Mars is to accept not a single duration, but a spectrum determined by the physics of motion and the ambitions of exploration. With that spectrum understood, the final step is not to measure the journey any longer, but to consider what it means to stand within such distances, looking outward at the worlds that wait. You stand on a planet that spins beneath your feet, circling a star that anchors your entire sky. The journey to Mars is not a challenge of courage, speed, or daring. It is a conversation with gravity, geometry, and time. You learn to move not as a traveler crossing a landscape, but as a participant in an orbital system that existed long before spacecraft were imagined. The distances are vast, the process is slow, and the logic indifferent to human impatience. From Earth, Mars looks simple, an ochre dot sliding through constellations. It offers the illusion of proximity, as though a longer leap or stronger engine could close the gap. But as you follow the route in thought, the skies widen. The sun becomes a reference frame. Orbits become highways. Months are not delays, they are properties of motion. The question dissolves from how far into how do objects move when nothing holds still. You begin to understand why mission planners choose windows, why spacecraft glide instead of sprint, and why arrival is a choreography rather than a landing. You see how every stage departure, burn, mid-course correction, insertion, descent depends not on forceful will, but on quiet alignment with physics. Mars is not a destination approached like a mountain peak. It is a world that must be met in orbit, on schedule, along a path dictated by the Sunday. And when you finally imagine standing there, red soil beneath alien skies, you glimpse something subtle. The accomplishment is not that a machine crossed millions of kilometers. It is that a species learned to listen to the rhythms of its own star, to read the patterns of motion, and to navigate distances that no instinct could ever comprehend. In that understanding, Mars becomes not a frontier, but a proof of knowledge, a world encountered through patience, mathematics, and the steady unfolding of the cosmos.